Chapter 12, Section 3. Standing waves. So at the end of Chapter 11, we learned about standing waves just as a characteristic of waves. So a little review about that, and we'll see how sound waves can also have standing waves and what that means. So standing waves on a vibrating string. The vibrations on the string of a musical instrument usually consist of many standing waves, each of which has a different wavelength and frequency. The greatest possible wavelength on a string of length L is where the wavelength equals twice that length. Let's look at the diagram right down here that they are illustrating this fact. We have nodes at each end, and we have one antinode here in the middle. That is exactly half of a wavelength. If I continued it on to get one full wavelength made out of this, we can see that crest and trough making one full wavelength. But the standing wave, the first time we can get a standing wave, is going to be one antinode, which means the wavelength is as long as possible. It's twice the length of our string, 2L. So this is called the fundamental frequency for that string. Fundamental frequency corresponds to this wavelength, the lowest frequency of vibration. So since we know velocity equals frequency times wavelength, that is rearranged to solve for the frequency, and that gives us the velocity of the wave divided by the wavelength. And if it's the first frequency, or we call it the fundamental frequency, then that first wavelength is equal to twice the length of that string. Velocity divided by 2L. L will be the length of that string. So this is our fundamental frequency that we can hear. So a little video about the fundamental frequency. Get my volume turned up.
On a given string of length L, standing waves exist only at certain wavelengths and frequencies. The lowest frequency at which a string can vibrate, called the fundamental frequency, is determined by the fact that the string is held fixed at its ends. The fundamental frequency of a vibrating string is produced by a standing wave that has a wavelength twice the length of the string, as shown here. Other standing waves that can be supported are simply integer multiples of the fundamental frequency. The sound of an instrument, such as a violin, is due to many of these frequencies being present when a note is played.
So there at the top, and let me switch over. I want to see if I do have that one later. All right. So let's move on. And we will come back and talk about some of the details on that in just a moment. The Harmonic Series, they just talked about the other standing waves that can occur are integer multiples of this wavelength. So if we look at the top row there, there's F sub 1, our fundamental frequency, or the first harmonic it is called. And then if I have twice that frequency, the wavelength is half as long as before. In fact, we are seeing one complete wavelength in row number 2. So look back at the wavelength for row number 1. It's twice L, 2L, twice the length we're seeing. Row number 2, our second wavelength, equals L. And if we go to row number 3 here, this is 3 times the original frequency, or 3 times the fundamental frequency, called the third harmonic. The wavelength here is only 2/3 of the length we are looking at. We are looking at 1 1/2 wavelength, so one wavelength is only 2/3 of that. Row number 4, 4 times that frequency, we are seeing 2 complete wavelengths here. So one wavelength is only 1/2 the length of that string. It's called the fourth harmonic. So a little bit more about harmonics, or the Harmonic Series.
The harmonics of any vibrating system are the frequencies of the standing waves that can be formed by that system. The first harmonic is the lowest frequency and is produced by the standing wave that has the longest wavelength, which is 2L. The second harmonic is the next lowest frequency and is produced by the standing wave that has the next longest wavelength, which is L. All the harmonics of a system have frequencies that are integral multiples of the fundamental frequency.
Let me replay that. Their audio is actually behind their video. So let me talk over this just a little bit. Let me turn the volume down and talk over that because their audio was not matching the video that they were showing. So here's our fundamental frequency. We have a half a wavelength, 2L is one wavelength. Here is our second harmonic, 2 times F1. That's one wavelength being shown. Here's 3 times the fundamental frequency, the third harmonic. The wavelength is only 2/3 of the full thing. They showed us 1.5 wavelengths on that one. So each harmonic is an integral multiple, or you could say an integer multiple, 1, 2, 3, of the fundamental frequency. So those things are called harmonics. So a harmonic series is the series of frequencies that includes the fundamental frequency and all the integral multiples of that fundamental frequency. So on a string, the harmonic series, which is formed by these standing waves, and the standing waves are the waves that vibrate that then we hear, because they're as a tone, a note, because they're a consistent frequency. On a string is just n times this V over 2L. Because the first time we hear it, n is 1 times that fraction, just V over 2L. And n becomes these integers, 1, 2, 3, 1's the fundamental, 2's the second harmonic, 3's the third harmonic, etc. So we multiply those frequencies all out and we get the harmonic frequency, harmonic series. There's 1F, 2 times, 3 times, 4 times. When we double the frequency, we are going up an octave. So in our last lecture, we had 256 hertz and then 512 hertz. And 256 hertz, let me get my tuning fork out and ring that one. That's middle C. Double 256 and we get 512, and that is C 1 octave up, doubling the frequency. Let me see if I can ring them both and bring them both up there so you can hear first one and then the other. 256, 12. So they should be 1 octave apart when I double the frequency. When I double the frequency again, which would be going here to here, that would be another octave up. So part of the harmonic series occurs between those 2 octaves. At the bottom of this, here is a link to a YouTube video about standing waves. So I want you to pause this video, go back to Google Classroom and the PDF that shows this capture. Click on that standing waves link so you can see the YouTube video about standing waves and sound and harmonics. Okay, you should be back now. This is an image of an oscilloscope, which is going to identify frequencies that are heard. So we have somebody humming, or the tone of middle C. So I probably should not attempt. I'm not going to attempt to hum middle C, or the tone of middle C, but this was captured from that. Now, in the voice singing middle C, you hear other harmonics. But it happens to be the first harmonic that we hear that we identify as the note that is being sung. We'll talk about the presence of the other harmonics and what that means. But you notice that 256 hertz, there is the first one that is being sung. There's a spike at 512 as well, a spike at 768, 1024, and these are just integral multiples of that 256. So we have not only the fundamental frequency here. The 256, middle C is being sung, but there's the second harmonic and how intense it is. The third, much less. The fourth, barely there. The fifth, a little bit more. The sixth seems to have disappeared. The seventh, etc. The eighth, and the ninth is kind of a mess down there. But you can see different intensities of a harmonic series that are present when a person sings one note, middle C. Air columns can have standing waves. Now your voice is kind of like a string. You have vocal cords that are vibrating, so it's kind of like a string that's going on there, but it's also captured inside a tube in an air column in your throat. So, standing waves and air column. Now you know you can produce tones or notes in an air column, not only from wind instruments, but if you take a bottle and you blow across the top of that bottle, and you'll get a tone in it. And if you have a liquid, maybe it's a water bottle, a different length column of air in there, different amounts of water, will produce different tones when you blow across the top. Those are actually standing waves of air inside that column. So let's look at the two situations in air columns that we can produce standing waves in air. So if both ends of a pipe are open, then that means there is going to be an antinode at both ends of this air column. So come down and look at this graph of two sinusoids here. Let's act like this is a tube. Right here's the top and bottom of that tube. And if my tube ends where I have an antinode of a vibrating air column, it will resonate right there. And we hear a tone, a note. Now that happens to be half of one wavelength. If I started looking at a wavelength here, I've just gone from the crest to the trough. And I would have to keep on going all the way over to there to get one wavelength. So it will resonate at 1/2 a wavelength, just like a string resonates the first time, vibrates naturally at 1/2 a wavelength. Now, let's see if we can analyze why we say we are going to have an antinode at each end of that column. Remember that in air, our wave is a pressure wave. So an antinode is where the pressure is fluctuating the most. And at the open end of that column, since it's open to the air, it's allowed to move in and out. The air is allowed to move in and out freely because it's open, and it can compress and rarefy freely. So open ends of pipes will have antinodes on them when I have a standing, vibrating air column in there. So since it is 1/2 a wavelength, the first time that this can occur, just like for a string, we have the identical formula for open-ended pipes, for strings, and both ends open. Integral multiples, so multiply it times 1, 2, and 3, and you get all the frequencies that can resonate. So if we look back down here at our picture again, the next time I can resonate is extending my pipe down until I get to another antinode. I need to arrive at another antinode. And I'm looking there, that's twice as long as what it was before, which happens to be exactly one wavelength that is going on. Next time I can resonate is when I get to another antinode. Extending my pipe down to this length, I can resonate again. Won't resonate in between. At that note, a different note would resonate because it has a different wavelength. So, first one was 1/2 a wavelength, then 1 wavelength, and then 1.5 wavelength. Or if we want to think of it, it's 1/2, 2/2, 3/2, 4/2 would be the next one if I put on. So 1, 2, 3, 4, we can multiply by every integer. So all our series, a complete series, times 1, times 2, times 3, a complete series is going to be shown on open-ended pipes. And the top part of this have a black ellipse, oval, around the top part of it. It's illustrating harmonics on an open-ended pipe. So open-ended pipe in instruments, a flute behaves this way. Because a flute has a hole that you don't seal off when you play your flute. It's open where your mouth is, it's open on the other end of the flute, and so your notes are formed by pressing your fingers down on holes that change the length of the air column is what's going on. And different length air columns will produce a whole series of different length notes played at the same time or one at a time. Pipe organs can have pipes that are open-ended. There's an opening right down there. It might be little, just like on the flute where your mouth goes, but it's open. So it allows an antinode, air pressure, to fluctuate freely there and at the other end. So that first diagram is the fundamental frequency showing half a wavelength. And then the next one, they get to the next antinode, so we have to be antinodes at either end. The next one proceeds to the next antinode available. So that's an open-ended pipe, which means open at both ends when we say an open-ended pipe. Now, if we close one end of the pipe, which is really what's happening when you're blowing air across a bottle, the bottom of that bottle is closed. It's not open at both ends. So let's come down here to where we are closed at one end. So if we are, did I circle the wrong? Oh, their image doesn't look very, oh, there we go. We're closed at the top. We're closed at the top. There's what we are. Closed at the top. Still open down here. We have to get air in some way to begin vibrating back and forth. So the closed end is fixed. Air is not free to move in and out of that. So it is going to be motionless essentially at that point. So it's a node. An antinode at open ends. So if we look down here at this illustration, here's my pipe of my sinusoidal curves down here. Here's the closed end of it with a node right there. We are not allowed to move. The air cannot move in and out there. Open ends resonate at antinodes, so we can resonate very quickly. Only 1/4 of a wavelength, and we can start resonating. If I outline, I have only gone 1/4 of a wavelength there. I would have to keep going all the way to here before I have completed one full wavelength. So I resonated there. Now the next time, if I extend my pipe, I can't resonate again until I get to another antinode at this open end. So as I travel along, waiting for my next antinode, that is 3/4 of a wavelength when I arrive there. Extend my pipe, there's one full wavelength, can't resonate because that's a node, until I get to another antinode again, right down here. 1 1/4 wavelengths, or 5/4 wavelengths. So if we look at these values, if our fundamental frequency occurs at 1/4, multiplying by 2 would be 2/4 or 1/2, but it doesn't resonate there. It's not until I multiply by 3. And then 4/4, 4/4, or 1, I don't resonate there, but 5/4 I do. So notice we are at odd multiples of the wavelength that we have. And this time the wavelength is only 1/4 of the wave, the distance is only 1/4 of the wavelength when I first resonate. So it takes 4L, down here in our formula, it takes 4 times the first resonating length before I have one wavelength. So my formula for a closed-end pipe, one end of a pipe is closed, there's a node at that one end, and we only will resonate at the open end when there's an antinode. So this is only going to occur at odd multiples, which means there are only odd harmonics. 1, the fundamental, times 3, times 5. Only the odd harmonics of the series will be available on an instrument that has a closed end at one end. So if I play a note on that instrument, the combination of harmonics that will be heard are only odd. On a flute, the combination of harmonics that can be heard can be all of them. So when I play a flute, middle C, when I play a clarinet, where I've closed off one end, squeezed my mouth against that reed, the flute and the clarinet, both playing middle C, sound differently. And we'll get at the end about why do those things sound differently. So two different formulas, depending on I have both ends open or one end closed, pipe closed at one end. And remember, both ends open and a string are the same. If you look at 423 in your book, problem number 2, here is the work that goes with it. They say we have the length of 66 centimeters, which is 0.66 meters. We need to make sure we convert it to our fundamental unit of meters. Velocity of air here, or in the string, is 340 meters per second. So the type of instrument that we have determines the formula that we are going to use, and in this case, it's V over 2L. So if I want to know what is the fundamental frequency that will occur, so velocity 340 of the sound on that instrument divided by 2 times the length, 0.66, rounded to 2 significant figures, we have 260 hertz. And then what we do really is just start multiplying that 260, which is the 2 significant figures, by 2, and then multiply it by 3, so that we pick up what frequency is going to be our second harmonic, our third harmonic, etc. First 3 harmonics are going to be at those frequencies. Timbre of the music. That is the music quality. The timbre of a flute is different than the timbre of a clarinet, which is different than the timbre of my voice, which is different than the timbre of a trumpet, a violin, etc. So they all play middle C, but they all sound different, and you know whether it is a flute playing or a clarinet playing, or maybe you do, because the timbre is different. The quality of that tone sounds different. And it's different because of the resulting combination of harmonics and how loud or intense those harmonics are. So if we jump all the way back to this diagram that we saw earlier, somebody humming middle C, all those harmonics that are present add to the timbre or the quality or what that middle C sounds like in that voice. And the combinations that are present and the volumes of those combinations that are present, or the intensity, will provide the timbre. So every instrument has its own unique combination of harmonics when you play a note. Clarinet sounds different from a viola because the difference is in timbre, even when both instruments are sounding the same note at the same volume. The rich harmonic of most instruments provides a much fuller sound than that of a tuning fork. If we did a tuning fork, all we would see is that one fundamental frequency right there. Tuning fork is just going to play one. It's not going to play more harmonics with it. It only is one. Very pure tone, but there's no depth or richness to that tone. So if I play a tuning fork here, very pure tone, but no richness to it. So if we have a tuning fork, a clarinet, a viola, they are all playing the same frequency or the same note, but they sound different in timbre. So here they're illustrating the clarinet, the harmonics that are present. First harmonic is the note we are saying it is playing, that we identify at it. Here's the intensity of the second, the intensity of the third harmonic, barely the fourth, barely the fifth. There's no sixth, a little more of the seventh. And that combination then, if we looked at the waveform, looks like this. Kind of looks like a mess out there maybe. But it provides the quality, and it is the same note. Come back up to the top one, my tuning fork. So there I have one wavelength, and then here comes 2 wavelengths, and there comes 3 wavelengths, and another half that is shown. We'll have that same basic outline down here. I have 1 wavelength, I have 2 wavelengths, I have 3 wavelengths, and another half. It's the same general form, the same note, but all those other little harmonics add character to it. The viola, the bottom one. So our viola, I'll circle it in red, playing the same fundamental frequency, it evidently has a second harmonic almost or the same intensity there. Third harmonic less, little fourth, little fifth, little sixth, way out there, little ninth. And these combinations of harmonics makes the viola sound like a viola. And again, if we look at the waveform down here, even though it is more complicated, let's see if I can pick out, there's 1. There is 2. And they messed up 3. They should have another half of it down there so it matches all the others. But it is repeating itself. It has repetition, same waveform repeating itself at the same rate as the others. Therefore, the same waveform repeating itself is the same note. I captured a trumpet. I was told it was a B-flat trumpet. I do not play the trumpet. I am not expert in that. They said they were playing a G, which means an F, so you musical people maybe know what I'm talking about, because I don't know what I'm talking about. But look at this waveform of it. And you can see it's not this smooth sinusoidal waveform. It has this character to it. But we have a repeat. There's one wavelength. There's a second wavelength. There's a third wavelength. It's repeating itself, the same pattern over and over again. I put in red one of them and then blue right beside it. Same wavelength, just a more complicated pattern. So it is playing a note, its harmonics combined to give the timbre or the quality of sound that a trumpet has. We recognize it as a trumpet. So a whole orchestra plays, same note, but we can pick out these different instruments. There is, let me make sure I didn't miss something up here. Timbre, I did miss something up here. Let's look at the timbre. Oh, forgot to turn my volume up after I turned my volume down. So let me turn my volume up and try it again.
Each musical instrument has its own characteristic mixture of harmonics at varying intensities. A tuning fork produces a pure sine wave with no harmonics. A viola string playing the same note as the tuning fork produces several harmonics, as shown in the graph. Each harmonic is itself a sine wave, and they add together to form a resultant waveform. The presence of these harmonic frequencies in the vibrating viola string produces a more complex waveform than that of a tuning fork. The difference in the two waveforms causes the tuning fork to sound different from the viola, even when both instruments are playing the same note at the same volume. Because the harmonics of musical instruments vary from instrument to instrument, every instrument has a different sound quality. This sound quality is known as timbre.
Beats, next topic. When two waves of slightly different frequencies interfere with each other, this interference pattern varies in such a way that a listener hears an alternation between loudness and softness. This variation, soft to loud, is called a beat. So in other words, a beat is a periodic variation in the amplitude of a wave. That's the superposition of two waves of slightly different frequencies. Remember, superposition is the combination of two waves, same place, same time. So look at the beats right here, go through that. Then, well, let me start with this one first of all. Here I have graphed, it's in red, a sinusoid. Sine 3x happens to be the problem. My G function is 3.3x, slightly different, just slightly different there. And you can notice regions where they almost match up, where they almost match up. So right near the origin, you notice them perfect, matching up. So if they match up, that would create a large amplitude. But then as I move away, and if you look right at 10 on the horizontal scale, you can see where they're opposite each other. They're canceling each other out. So my h of x, my third function on the row, is just the sum of the other two. And notice what happens. There at the origin, 0, they are constructively interfering, large amplitude. Then that amplitude disappears down there at 10, increases again at 20, disappears down at 30. So I have these large and small amplitudes, constructive and destructive interference. My large amplitude is a tone that I hear, and then that tone disappears, and then that tone comes back. So we'll look at their little video about it, and then we will listen.
When two waves of slightly different frequencies are present, they can interfere. The interference pattern varies in such a way that a listener hears an alternation between loudness and softness. The variation from soft to loud and back to soft is called a beat. One beat is shown here. When the two waves are exactly out of phase, destructive interference takes place. The two waves cancel each other out, and there is little or no sound. When the two waves are exactly in phase, constructive interference takes place. The two waves add to a large wave, and there is a louder sound. As the sound continues, the waves continue to produce destructive and constructive interference, giving beats. Piano tuners use beats to tune piano strings to a reference note from a tuning fork.
So we'll talk about tuning in a minute, especially for those who are in band, but I'm going to play some tuning forks here. So here's the first one. So get that tone in your head. Now here's the second one. Now that was a very similar tone, but they're not exact. So let me play the first one again. Second one. Just slightly off, if you can pick that up with your ear. But now watch or listen to what happens when I first hit the first and then the second. Those are beats, that alternating loud and soft. The wah, 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 those are beats. So if we are trying to tune an instrument, let's say we pick on the flute players in band and we get them to play a note. The first flute, the first flautist plays a note, and then the second chair plays that same note, and you hear this. They're not quite in tune. And so we try to tune a little bit. Now I'm going to adjust one of my tuning forks. Even faster. What that means is I am farther apart in my notes. I'm tuning the wrong way. So let me try it again. You might have heard just a slight variation, but they were fairly close to each other. I'm getting in tune. Much slower, that's all I'm going to illustrate, much slower, but I'm in tune when the beats have disappeared. To finish it up, there's a YouTube link down here for beats. So this is actually the end of this instructional video, so you can stop this instructional video, go to the PDF, click on that very last link to see a link about beats. And section 3 is where your homework is from.